Bismillahirrahmanirrahim. Greetings. In this lecture, I'm going to present another kind of limit which is a bit different than those that we have covered in the previous lectures. Now, as an aside, and for background kind of knowledge, I would like to say a few words about some properties of a sine function. So let's get started, shall we? Now, I have written them large enough with the map, with the marker, but I still zoom it for you so that if you like to take notes. But I go orally over them right now. Now, we know that sine, we are familiar with them, they are very elementary, these properties. We know that sine is a periodic function, which means keep repeating itself, and the period of that is 2 pi. And then we also know that the sine function is bounded above by 1 and bounded below by -1. So it's a bounded function. What else we know about that is that its domain is the whole entire real numbers, the domain of that. And the range of that, as I already said, is bounded between 1 and -1. So the range of that will be the interval from -1, 1, the closed interval. And then we go that its maximum occurs, its maximum point occurs as a odd number, odd multiples of pi over 2. I repeat myself, the maximum and minimum points of the sine function occurs at odd multiples of pi over 2. In fact, 2k, 4k plus 1 are the multiples that k is an integer will give us the maximum point, which is bound, and 4k plus 3, where k is an integer, will give us the lower point, which is -1. And the zeros of sine function occurs at even multiples of pi over 2. So pi over 2, it seems that like playing very important role in kind of better comprehending the graph of sine function and also assisting us in sketching the graph of that. Now, I have written all of them as I mentioned. I repeat myself. I will zoom it for you if you like to take time. Now, I am giving some hint about sketching the graph of the sine function. So in order to sketch it more artistic and more clear is to divide the number line, as long as you want to go, into multiples of pi over 2. Multiples of pi over 2. So you start with, if you are going to the right of 0, so you start from 1 pi over 2, you can make, you can use, what is it, if you want to put it, the ruler is about 1.57 units, millimeter, or whatever you may select. So then next one will be 2 times pi over 2, which is pi. Next one will be 3 times pi over 2, which is 3 pi over 2, and so on and so forth. So you go with the multiples of pi over 2. All right. Now I have written them I've said that how to partition the set of real number, the x-axis, into multiples of pi over 2. Now, I have written all of them, I have already gone over them, and so the set of all sine of 4k plus 1, multiples of pi over 2, where k is is an integer. So multiples of them. So for example, if k is 0, you get 1 pi over 2. When k is 1, you get 5 pi over 2, which is again the maximum. And the next one, and next one, and next one, you can go over them. Now let me, with your permission, to zoom this one. May I? Okay. Now, when I zoomed it, you can always pause because you have upper hand with your computer, you can always pause and take notes in case if you like to take notes. All right. Now, what I said, just I go over that one more time quickly. As a graph sketching, is I divided from 0 to wherever you wish to go, I divided into multiples of pi over 2. So you can see it's 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, 6 pi over 2, and so on. The odd multiples of pi over 2 give me the maximum and minimum. 1 pi over 2, for example, is here, that's the maximum. Then 3 pi over 2 is negative 1. Then again 5 pi over 2 is my maximum. And these points and also zeros are the even multiples of pi over 2. So it's 2 pi over 2, which is this one, then 4 pi over 2, which is this one, 6 pi over 2, which is this one, and so on and so forth. Now we can go ahead and sketch the graph of it, very precisely, just connecting these few points. It's a wave, and in the wave theory, in fact, the graph of sine and cosine functions, they play a very important role. The entire physics and quantum mechanics is really based on wave theory, which comes from the graph of sine and cosine. So they play a very important role in that regard. Okay, now we are familiar with that. I don't think I need to zoom it for you. I think it's clear enough and it's too elementary. You are all familiar with that. Okay, then after this, let's start the main part of today's lecture, which is to discuss about the graph of sine of 1 over x as x approaches 0. So I have written here for you, and I may zoom this one because there is a set in here that is very important to be aware of. Now, this one is not too visible. Is a function f of x is the sine of 1 over x. It's not sine of x. You can see that I made a little bit kind of messier. Okay, the domain of this function is all real numbers, naturally, except 0. We don't even have to mention it because if the denominator of a function is 0, we are not dealing with number to begin with. And then we say let x assumes its value from this set. Now we have very good important point for selecting that. It's very clever selection. It's very interesting, intelligent selection. So let S to be the set of all x such that x equals to 2 over k multiples of pi. So it's 2 over k pi. But naturally k cannot be 0. Other than that, k can be any integers. And I have said that k is any integer except 0. I don't even have to mention 0. Then as the absolute value of k, because k can be positive or negative, so I put the absolute value of that. As the absolute value of the k increases, that arrow indicates as increases, and I put it in word, I and C, meaning increases without bound, which means keep going, then the value of x decreases, approaches 0. Now at the first glance, for the kind of beginner student, they may say, just 1 second, if x approaches 0, that is going in fact to happen, as x approaches 0, then 1 over x approaches infinity. You may look at it that way, but the function sine does not permit it to go to infinity, because sine is a bounded function. It's between what? -1 and 1. 1 and -1. The maximum get is 1. The least you can get is -1 and assume all other values between. So don't think about that as x approaches 0. 1 over x approaches infinity, so we are kind of in difficulty, you may think to, at the first glance, but again, I repeat myself, sign does not let it to happen. Sign always controls that between 1 and -1. Okay, let me zoom this one as I mentioned. Okay, when I zoom it, you can pause it and write notes. The set that I mentioned is going to play an important role in our today's lecture. Now, I have written this one now for you. I don't know if I should also go ahead and zoom in. Let me see what I can come up with. Now, we select our values for x. X is approaching 0, so we can select any number we want. As a matter of fact, I did select some good points for that. I don't know if I had that one. I don't know where it is now. No, as x approaches 0, you can select numerical number, half, 1/2, with the calculator, find the sign of that. But I am selecting my x's from the set that I mentioned. I'll zoom it for you. It's very important set is in this lecture. So for a special purpose, I'm repeating myself, it's a very kind of clever and smart selection. Now, here the selection of the values of x from the set S, we call that set S, as x approaches 0, the interval, the intervals were consecutive, is that right? The one that I write, pi over 2, then 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, the intervals that we have. Now when we select our values from the set S, the length of those intervals start to shrink. You will see that when I look at the graph of that. And I repeat myself again, selecting our values of x, because x is an independent variable. So we are permitted to select any values we want in the domain of the function. So we select purposely our values for the x, the values that x can assume from the set S that I already zoomed it for you. All right. So this is what this is indicating. So we are very clear with this one. Now, I have made some numerical. At this one, I suppose you don't need any zooming. Is written large enough, and I just go over them. Now here, these two are for the sine x, and these two, the x is not same x as this one. This x is belong to this function, so don't confuse them. And I put kind of in a box red so that you notice it. Now, this x, I'm giving values for the sine. So I'm starting with pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2, and so on and so forth, that I have already mentioned. And as you can see, the sine function is going to assume its maximum, minimum, and its zeros. Zeros of a function, it means the point that the function hits the x-axis. We call it zeros of that function. So these zeros of sine functions are what, look at this one, are even multiples of pi over 2. So as you can see that when I give this kind of numbers, this selection of numbers for my independent variable, sine of x is going to give me 1, 0, -1, 1, 0, -1, 1, 0, -1. And I can point them and connect them as I already sketched the graph for you. Now, the point is that here, as you notice, the x is increasing. Is that right? Look at that, pi over 2, then 2 pi over 2, 3 pi over 2, 4 pi over 2. It's increasing, going to infinity. That means what? That means the inverse of them, if we give to the value for x start to decrease. Do you follow me? And the reason that I repeat myself, that is the values we are selecting for the x in this in the form of a sine of x equals 1 over x, purposely, for what reason? For this particular reason. Now look at that. If I select my x's as 2 over pi, then 2 over 2 pi, then 2 over 3 pi, all of these are the inverse of them. So 1 over 3 pi over 2 is same as 2 over 3 pi. So from this, when I was given this value for x, x was increasing, and therefore the inverse of that will decreasing. So if x approaches infinity, 1 over x approaches 0. Is that right? Here it is, x is approaching infinity, therefore 1 over x approaches 0. And these values that I have selected for x, for this x, are what? Are approaching 0, because they are all inverse of them. Each of them are inverse of their corresponding for this one. Do you follow me? That's very beautiful observation. I repeat myself one more time. The domain of the sine function is real number. And domain is what? A set of all independent variables. So it is independent, and we can select any numbers we want from the domain of the function. So in this case, we are selecting the values that x can assume in the domain from the what? From the inverse of each of them, because as they increase, the inverse of them is decreased, and that's exactly what we are after, because we are saying what happens when x approaches 0. Do you follow me? So when I select this one, look at this one. The x is approaching 0, because I'm selecting these values for x, but 1 over x will give me this kind of number. Will give me this kind of number, 1 over x. And sine of 1 over x, which means I'm selecting sine of these values, sine of these values, sine of these values. Because 1 over this is this. Do you follow me? There are kind of two inverses involved. Now, sine of, for example, if x is 2 over pi, then 1 over x is pi over 2. X is small, but I'm working at 1 over x will be pi over 2, and sine of pi over 2 is 1. And look what happens. I'm getting exactly same points here. 1, 0, negative 1, 0, 1, 0, negative 1, and so on and so forth. Now the advantage of that is that I can put them on the x-axis, and now the value of the value that are selected for the independent variable for x now is decreasing, approaching towards 0, but a special selected of them approaching 0, and the interval between two consecutive zeros of this function sine of 1 over x, the interval between two consecutive zeros approaches 0, gets smaller and smaller. You follow me or not? Now please pause, think, reflect, contemplate, don't rush, and then come back again, because you have upper hand with your computer. So try to fully comprehend what I just said. It's very, very beautiful, intelligent, and in mathematics you have to know this kind of tricks, this kind of manipulation, so that the subject become much more clear to you. Okay, now let me do what I just said and put it in a sketching graph. No, I don't think I need to let me do it, just for the sake of it, to pause it. Okay, and let me know. Go to what I just said for the graph of that, if I may. This one I may need to zoom it. It looks like it's a small. Now look what happens. I selected my point here. I'm selecting my points from what? From the set S that we have gone over that. And look at this, the lengths of the interval are starting to shrink. You see that? They get smaller and smaller as we get closer and closer to 0. That means the sine wave start to become more rapidly oscillating as we get closer and closer to 0. So let me just sketch it, if I may, graph it. Now, let's say I start here. This is the zero of my function. This is negative 1. And this zeros again. This is positive 1. This is these zeros. This is negative 1. Again, this is going up and then coming down. And then up. And then coming down, going up and coming down, and so on and so forth. As you can see, I start to oscillate so fast. No matter how great artist you are, how precise you can possibly sketch this one, you can never do better than what the computer can do for you, the machine can do for you. So I have the graph of that I'm going to put. I'm going to zoom this one if you want, and I have the graph of that one from the computer, and as you can see, it's very nicely fantastic, artistic, how precise it is. As you can see, the maximum is always reaching 1, the minimum is negative 1. Now they are not, of course, in a scale, because they are kind of visual aid. This is not analytical geometry that we have to be in a scale. So we are not drawing them in a scale, but to give the concept, to comprehend the concept better. So you can see that this one, I may zoom it with you for you. Okay, now here as x approaches 0, what happens? Look at that. The closer we get to the 0, the sign of 1 over x start to get 1, then get 0, then negative 1. We get a little bit towards 0, immediately the graph jumps to, let's say, 1. We go a little bit to the left of it again, immediately jumps to the negative 1. And of course it's continuous, so it's going to hit the x-axis. So it's going to assume 1, negative 1, 0, negative 1 as we get closer and closer. And it's very, very slippery. You cannot control that. You closer you go, it jumps 1. Closer you go, it jumps down. The closer you go, it jumps up and down, oscillate. So no way you can say what value is approaching. You can say approaches 1, because it's not, when you get close to 1, immediately jumps to negative 1. You can say it's approaching to negative 1 because when you go close to negative 1, when you go a little bit to the left of that, immediately jumps to 1. So no way you can control that one. It's going to oscillate up and down. So this limit is different than the kind of limit that we discussed in the previous lecture, that was absolute value of x minus 2 over x minus 2, which the limit of that from the right hand side was 1. The limit does exist, is 1. And the limit of that from left hand side was negative 1. So the limit exists from the left hand side. But since these two were not same numbers, so we concluded that the limit does not exist. But this one, from right, we don't have no limit. From left, we don't have any limit also, but we know it's bounded. It goes up and down, up and down, up and down. It's very interesting kind of function, sometimes for as a counter example to give when you take more courses in calculus, to use that one. That is, the oscillate and the limit in that sense does not exist. Okay then, I thank you for watching, and next lecture I'm going to kind of close all these 4 or 5 lectures I have given, so that to improve your intuition about this concept of limit. And then after that I may go to the let's say conceptual definition of limit in a sense. And after that should be short. And after that I'm going to go to the rigorous mathematical definition of limit is known as epsilon delta definition of limit. That was all the subject is about, and try to filter away the abstract part of it. And then we go through the theorem, related theorem, and then some problem we solve, and at the end hopefully the abstract part of the epsilon delta definition is absolutely out. I repeat myself one more time that most of the students in especially taking calculus for the first time, they have difficulty with epsilon delta, and being honest to you, sometimes even graduate students in mathematics they have difficulty. One reason is that they didn't cover them in undergraduate because the instructor, the professor knows the student have difficulty with that and they kind of bypass it. And that was in my case when I was taking undergraduate. So when I took a graduate course in that, that was the first time I was being exposed to epsilon delta definition of limit, and I did have some difficulty before I adjust myself. Okay, then I thank you for watching. I wish you all prosperity and good health, and please stay safe. So long.